To answer this question, let's look closely at the data. It seems that the red and green dots are nicely separated by a line. Here's the line, and we can see that most points over it are green, whereas most points under it are red, with some exceptions. So that line is going to be our model. And from now on, every time we get a new student, we check their scores and plot them in this graph. If they end up over the line, we predict that they'll get accepted. And if they end up below the line, we predict that they'll get rejected. So since student 3 ends up here, at the point with coordinates 7 and 6, which is over the line, we conclude that the student gets accepted. So if you said yes, that's the correct answer. This method is known as logistic regression. And now the question is, how do we find this line that best cuts the data? So let's look at a simple example. How do we draw the line that best separates the green points from the red points? Well, again, a computer can't really eyeball the line, so we can start by drawing a random line like this one. And now given this line, let's randomly say that we label the region over the line as green and the region under the line as red. So just like with linear regression, we'll first try to see how bad this first line is. A simple measure of how bad the line is just the number of errors. That is, the number of misclassified points. This line misclassifies 2 points, one red and one green. So we'll say it has 2 errors. And again, like with linear regression, what we'll do is move the line around, trying to minimize the number of errors using gradient descent. So if we move the line a bit in this direction, we can see that we start correctly classifying one of the points, bringing down the number of errors to 1. And if we move it even more, we correctly classify the other one of the points, bringing down the number of errors to 0. In reality, in order to properly use the gradient descent method, it turns out that the number of errors is not what we need to minimize, but instead something that captures the number of errors, called the log loss function. Let's actually study that in more detail. So here are our 6 points again, with 4 of them correctly classified, 2 red and 2 green, and 2 of them incorrectly classified, 1 red and 1 green. The error function will assign a large penalty to the 2 incorrectly classified points and small penalties to the 4 correctly classified points. We'll actually learn the formula for the error function in the class. Now we obtain the error function by adding all the errors from the corresponding points. Here we obtain a large number since the 2 misclassified points add a lot to the error function. Now the idea is to jiggle the line around to minimize this error. So if we move the line in this direction, we can see that some errors decrease and some slightly increase. But in general, when we consider the sum gets smaller since we've correctly classified the 2 points that were misclassified before. So the point of this process is to find the best line fit by minimizing the error function. And how do we minimize the error function? Again, with gradient descent. So once more, here we are at the summit of Mount Everest. We're quite high up because our error is large. Here you can see how the height is the sum of the green and red areas. So we explore around to see what direction brings us down the most, or equivalently, what direction can we move the line in order to reduce the error the most. And we decide to take a step in that direction. So now we're misclassifying only one of the points. We can see how that decreases our error function, bringing us down the mountain. And we do it again. We take a step in the direction that reduces the error the most. Now we're at the bottom of the mountain since we've reduced the error to its minimum possible value.